So up to this point, we've been focusing on normal distributions where we know that normal distributions have that bell-shaped curve where at the center we will find the mean. So the mean is 0 and we use a standard deviation of 1. And when we're looking at sampling distributions of sample means, the formula that we use to calculate z-scores is this formula here where the denominator, we don't use sigma, but we use sigma divided by the square root of n. And then we also talked about critical values. So let's remind ourselves of what a critical value is. A critical value is a z-score that separates extremely high z-scores from the rest of the distribution. So in this diagram below, you'll see that the blue curve represents the green curve. So I'll highlight the green curve here. The green curve represents the standard normal distribution. And so if I'm looking for a critical value is a z-score. So let's say that the critical value here is 1.96. That's a z-score that separates all the z-scores above 1.96. So there is a probability associated with those z-scores. So that probability is the area that I'm shading in red here. And that area corresponds with a specific critical value. So here, again, right? A critical value is just a z-score that separates extremely high z-scores from the rest of the distribution. But now we're going to talk about the t-distribution. So oftentimes when we are looking at data, it's very rare that we know the population standard deviation. So the population, I'm writing it at the top here, population standard deviation, the notation we use for that is sigma. So a lot of times if the population mean, so population mean, which we call mu, if this is unknown, then the population standard deviation is also going to be unknown. So if we don't know, if this is unknown, if we don't know the population standard deviation, then notice that I cannot use this formula here to calculate z-scores because this formula requires that I know sigma, okay? And if sigma is unknown, then I also can't use the normal distribution because the normal distribution calls for us knowing sigma. So what do we use instead? Anytime that you don't know your population standard deviation, so anytime you don't know sigma, it is unknown, this is when you want to use the t-distribution. So instead of calculating z-scores, we're going to calculate what's called t-statistics. So t-statistics are like t-scores. They act like z-scores, but instead of on the normal distribution, we're going to look at the t-distribution. And so here, notice that in the formula, we don't use sigma. There's no sigma. Instead, we use S, where S is your sample standard deviation. So we use sample data here. The nice thing about a t-distribution is that it is also bell-shaped, so it looks a lot like the normal distribution, but the main difference is because we are using sample standard deviations, right? The t-distribution is going to vary because every time we take a sample from the population, we could get a different sample standard deviation, which means that S is going to vary. So anytime S varies, the t-distribution is also going to vary. So on the left here, you'll see I've got two other curves. I've got this red curve and this blue curve. So notice that if we compare it to the green curve, which is the standard normal distribution, let's just first look at the blue curve. So the blue curve is the t-distribution where our sample size is 3. And I hope that you can see that the difference lies in the tail. So if we compare the blue curve to the green curve, notice that the tail is a little bit thicker. And so if the tail is thicker, then the area under the tail regions is going to be greater. So on the t-distribution, that's really the difference. The difference is in the tails. But it turns out that as n gets smaller, so if you take a look at when n goes from 3 to 12, notice that the red curve, right, the tail gets a little bit thinner. So here we can see that as we move from an n size of 3 to 12, the t-distribution starts to match up with the normal distribution. So anytime that we're working with the t-distribution, since we don't know sigma, right, what we focus on instead is what's called degrees of freedom. So your degrees of freedom, there's a formula for finding your degrees of freedom. It depends on the sample size. And that formula is simply to take n, your sample size, and subtract 1 from it. And then what we'll end up doing is we'll end up using, let me find my pen here, we'll end up using table A3 to find our critical values. Okay, right?